My name is Sergey Petrunya, and this is the Optimizer Trace walkthrough. Today we'll cover everything about the Optimizer Trace. So, Optimizer Trace, it's actually not a new feature. The initial prototype existed before MariaDB existed. It was initially released in MySQL 5.6, and the first release in MariaDB was 10.4 last year. After that we have added more tracing, got some experience of using it, so I think now it would be a good time to look at what Optimizer Trace and how we can use it. So before we discuss the specifics, let's discuss the goals. The goal of the Optimizer Trace is to show in details about what goes on in the optimizer. Typically the workflow goes like this. We get the SQL statement, it is optimized, then one can see the query plan if explained, then it is executed, and analyze for statements feature can be used to get information about that. But the optimization process has been fairly opaque, and now Optimizer Trace is used to provide details about what goes on here. And there is a lot. There are query writes, values, for example, view merging, there is very close analysis, search for query plan, finally query plan refinement. So if you have details about what goes on there, it allows you to answer questions. The most typical question is like why certain query plan is not chosen. If you have added an index and it's not being used without Optimizer Trace, it can be very hard to answer the question about why is this index not used. The second very common use case is why are query plans different across database instances. This is a fairly common question where somebody is upgrading from one database version to the other, or is just setting up another instance, and it has of course slightly different statistics because statistics depends on the data layout, or there are some minor DDL changes. It's like a column has now different collation. It was nullable and now it's not null, or vice versa. And these changes seem irrelevant, but one cannot tell with 100% certainty. And without Optimizer Trace, one had to just manually inspect all of the parts of the environment and try to guess why the query plans are different. While with the trace, you can just get trace on the old instance, trace on the new instance, and then see what the difference is. And this is much more efficient. Finally, the trace makes it easy to ask for help or report an issue to the development team. Because if having an optimizer and query optimization issue while uploading, your whole data set is not always possible. It can be too large, or it can contain some sensitive data. Typically you can provide explain or table definitions, but these are not always sufficient. While the trace is of reasonable size, it is also a text document, so you can view it and remove any sensitive information from it, and then submit it asking for help, or even if you think it's a bug in the optimizer, reporting it to the development team. So let's look at how one uses the Optimizer Trace. How does one get the Optimizer Trace? This is fairly easy. You just set this Optimizer Trace to 1, which enables saving the traces. Then you run your query. And after that, you do select star from information scheme Optimizer Trace, and one of the columns you get is the trace, which is a really long document with the trace. The traces are stored in memory. You can view only the trace for your session and only one last trace stored. So you need to do select star from Optimizer Trace immediately after your query. A query can be select it's typically better to use explain and pretty much any statement that can have a query plan. So Optimizer Trace contents, it is a huge JSON document. Basic idea is that it's a log of all of actions done by the optimizer. Now, I would like to say all actions and that you can see everything that optimizer did to your query, but unfortunately this isn't the case. The optimizer does a lot of things and not everything is traced yet. But I think we have a good subset of all actions, so all of important or typically like relevant actions are already printed, but don't expect to be it to be 100% description of what is your query. So why is it JSON? Well, JSON has two properties. First, it's human readable. It's easy to extend, so we can add more tracing as we go. The second is that machine readable. By that I mean that you can use JSON processing function to extract part of the trace. The most important ones are JSON extract, which gets the JSON document as the first argument, and then you can give it a JSON path expression to what you are interested in. And the output of JSON extract is JSON document, which we can pass to JSON detailed, which will print the JSON. So this way you can get a piece of optimizer trace, and optimizer trace is typically quite large. So it's quite useful to be able to get a small subset of it, and you don't need to resort to some crazy regrasp with grep. In case somebody are not familiar or don't have a clear idea what JSON is, here is one slide about JSON. JSON is a very simple simple language. Basically everything in JSON is value. A value is string in quotes, number, true, false, null. It can also be an object or an array. So array is input in square brackets, and it is a comma separated list of values. Now, values do not have to be of the same type. There is no data types, so you can start an array with string, then continue with number, then add a nested array, an object, and so forth. Members of the object is similar to array, but in the object the members are named. Here there's the first object with name, and then again the value, which can be anything, and so on. Typically the names of different members in object do not overlap, and this is the case for the trace. Okay, so let's look at what is trace contents and how to interpret. Before we do that, some generic background information on query processing and SQL databases. It starts with an SQL statement, then there is a process called parsing, after which there is a parse tree, which is basically what comes into your mind when you look at the query yourself. Then there is a process called name resolution, which finds for each reference to table or view, which finds which table in the database it is. So what is the column names, what are the column data types. So if you have column 1 equals column 2, which data type would be used for perform the comparison, and so forth. So this parse tree with resolved names, there is no established name for it, let's call it parsed query. Then there is query optimization, which comes up with a plan to execute the query, and you get the query plan as a result, and then you execute. So optimizer trace is primarily targeted at query optimization, but it covers a bit of name resolution because some optimizations, some rewrites were traditionally done in MySQL and MariaDB early there. They're not large, but still you will see some name resolution parts. And for the same reason, it covers a bit of execution, although it's mostly in MySQL version of optimizer trace, not in MariaDB. But still, what you can see in the trace, you will see for name resolution, you will see join preparation member, which lists things which are basically done at name resolution phase. And one other thing that is not done is that just first it prints the query. And then I think there is attempts to merge view, and some other initial rewrites can be found there. And you can also see there is a select ID equals 1, so this is done for the top level select. Then join optimization. This is the biggest element typically, and there are a lot of things here. And finally, there is join execution element, which is generated when it is executed. As we see here, that this is all for select ID equals 1. This is because each select is optimized separately. Well, there are exceptions to that. The select can be merged to its parent select, it can be converted to semi-join, and so forth. Then for each select, the optimization files is shown in the diagram. Although there is some exceptions, but the general workflow is that for each select we first do rewrites and transformations. Then we collect table information and table statistics. This is like preparing for the game. Then there is a main game join order choice. This is like the hardest choices the optimizer has to make. After the game is done, there is some fix-ups and plan refinement where we fix all the details, and this is, in the end, we get the query plan. So in the trace, this looks like this: join optimization, select ID, then there's a steps, which is an array of objects, and there are different objects denoting different things. As you see, there is always an unnamed objects because object can't have names. Then there is a name and either object or array. So the important ones are ref optimizer key uses. This is generating ref access. Rows estimation, then again, this is also an array that for each table there is, we collect table information by estimating number of matching rows. The main game, the join optimizer choices in considered execution plans. And as a result, you get this best join order. And then there are some other fix-ups or plan refinement steps, depending on what is in your query. So let's look at these elements. Start with ref optimizer key uses. Ref optimizer, let's try a query. Select star from T1, T2, where T1 key column equals T2 key column. This will give us an explain. It has put T2 table first, then there is table T1, and it uses index lookup, it uses key column, and it uses ref access. So a question one can ask, could this use the other join order instead from T1 to T2? Here T1.keyColumn is an integer and T2.keyColumn is a varchar of 100 with UTF-8 general CI. If you look at the optimizer trace, we will see ref optimizer key uses. It is an array that has only one element, T1 key call, and the value for it is T2 call. And note that there is no other vice versa. So we can make lookups one way. Interesting, let's compare that with the other way. What if both columns were varchars? Let's, instead of table T1, use T3 and write the same query. And here we see that lookup is possible in two directions. There are two entries. Here there was, well, if you know the optimizer well enough, you can guess that if in integer is compared to string, then they are compared as double values, and comparison of integers, which is this index is using, is compatible with that, while comparison of doubles is not compatible, because basically 0, 0, 1 is the same as 1 when you compare them as integers, but if you compare them as strings, these strings of 1 and 0, 0, 1 can be very far apart in different parts of the index. Well, but with the trace, you don't need to remember all of these details. You can just see that, okay, here there is a way to look up in table T1 from T2, but not other way around. This again can be looks basic and kind of obvious for these simple cases, but can get much less obvious for much more complex cases where there are complex where clauses and the optimizer makes certain inferences of them, and Believe me, even for the query optimizer developers, it's not always apparent whether the optimizer was able to infer some equality or not. The second interesting part is range optimizer. Range optimizer is a part of the optimizer which looks at the where clause and infers which ranges we may scan to find matching rows. And this inference can get quite complex. The first source of complexity is multi-component keys. Then there are also inference using equalities. If call1 equals T2 and there is call1 less than 10, the optimizer will infer that call2 less than 10, well, in most cases. And the problem for all of that, explain format JSON will just show used key parts, how many key parts are used. So let's take an example. Here there is a table some events with start date and end date, and there is an index defined on start date and end date. And then there is a query, okay, I'm looking for events with start date greater than June 24 and end date less than June 28. Like I want to catch an event sometime. And the explain will show you that 2 key parts are used, but you might be surprised at a very kind of slowish performance, or the range access is not used at all. And if you look into the trace, you will see that surprisingly the second key part is only using null. Now the discussion of that is sort of outside the scope of this talk, but basically to be short is that the optimizer is actually not aware that the end date must be greater than the start date. And if you let him know that by adding these conditions, then you will see that the range being scanned is much more narrower, and there are a lot fewer rows in it. Another example with multiple ranges. Now let's write a query where start date is one of these 3 days and there is just one end date. We will see that actually it generated 3 ranges, each of them using 2 key parts. Well, so far it's okay, but for longer or bigger in statements, there are this cross product of taking all ranges for key part 1 and producing cross product with key part 2 can cause some undesired effect against. So sometimes it will be useful to know how the optimizer was able to handle it, because it employs some aggressive techniques to reduce the number of ranges it is producing. Closely related to range optimizer is so-called loose index scan optimization. Loose index scan optimization is optimization used for group by queries. It can be quite useful. Loose index scan can be quite faster than other grouping strategies. The choice whether to use loose scan is cost-based, so it depends on the data statistics and also on the data from analyzed table. It also has quite complex applicability criteria. So let's take an example. Let's create a table T and create a key of 3 components, KP1, KP2, KP3, and let's set to 2 very similar queries. We do group by of KP1 in both cases. Then we want to find the minimum of KP2, that is for each group. And then there is a where condition, in this case on just KP2, and here it's on KP2 and KP3 also. And explain will show that this query is using loose scan while this one is not. And it's not at all clear why would that be so. Until you look at the optimizer trace, and here you see that the loose index scan is used, and here it is not, and it's usable false, cause key part after infixing the query. So now we see that the problem is not data statistics, the problem is not analyzed, the problem is that in loose index scan is not usable here. Good. So let's get to the next part of it, join optimizer. Join optimizer is the biggest, most important part of the query optimization probably. And it produces two objects. One of them is considered execution path, and the second one is the best join order. Let's take a look at the example. Let's get a join. This is tables from DBT3 benchmark. There are parts which are produced by manufacturer. There are suppliers, and in the warehouse you have parts that are available in the warehouse. And so we write a join with these join conditions connecting part to part soup and part soup to supplier. And then there are also where conditions on manufacturer, part manufacturer, on supplier's account balance. So we are looking at, we want to find parts from this manufacturer provided by the supplier from with negative balance, which we actually have in stock. And this is the explain. It shows the join order. Well, best join order will show us the join order as well. And considered execution plans object will contain a log of how the join optimizer has arrived at this query plan. Now it has a lot of content, so it's too much for the slides, or too much. It would be too much for the screen, so we would need to use grep. Join order is constructed in a top-down, that is first to last way, and there are two important member variables here. Plan prefix shows what is already constructed, and the table shows what we are trying to add. And the table always follows plan prefix, so if you just grep, if you just save the trace to the temporary file, and then we just grep for plan prefix and also ask it to print one row after the match. So this way we find that, okay, we started with empty plan prefix and added table supplier, then we added table parto, then we added table part soup. And this was, then we got back to the prefix of just table supplier, and added part soup, and added part after that. And this is, by the way, the join order that the optimizer eventually decided the best. But it didn't stop here, it also considered two other prefixes. It didn't, notice that here it didn't consider three table prefixes or full join orders. This is because the join optimizer aggressively prunes away. It tries to not to explore join prefixes which are not promising. And here we can actually already see which join orders, which prefixes were explored and which weren't. Let's look then at how join optimization proceeded for the join order here. So first, plan prefix is empty and the table supplier is first. If we search in the trace, we will find this one. Best access path is a function in MariaDB or MySQL source code which adds a table to the prefix. What it basically does, it considers various access types and it computes how many rows it will need to enumerate, what would be the cost, and then shows whether it's chosen or not. So here it chooses range access, which would produce this many rows. Yes, and it has chosen it. This is a rows for the number of output rows for the plan so far and the cost of it. Okay, so after the supplier, we get to part soup, prefix supplier, table part soup. That shows there are two ways actually to access it, ref access and full table scan. It picked ref access. And then there is a third one. Prefix is supplier part soup, and then we are adding table part. Again, there are two ways to read the table. We pick the ref access. And well, this is a good query plan without an issue, so we don't see any issues here. But in case you are wondering, is the optimizer considering to use certain index for this join order? Is it what estimates it's using? Here for the primary key, it's kind of obvious that there will be one match. For non-unique indexes, which have some conditions are constant and some conditions are not constant, the estimate here is computed with quite complicated computations, so it's interesting to see. If there is a where condition attached, the optimizer will try to estimate its selectivity and print it here, which this success rate of this, like say, varies a lot for not just for MariaDB. For this is a hard query optimization problem. So here, this is something the optimizer can get wrong. This is how it raise. Okay, so this is the third table part. So we know that how many rows the optimizer expected to see, what would be the cost, join output cardinality. Let's look at why didn't it pick the other way? We saw that it went from supplier to part-sup to part. How about part to part-sup to supplier? We start with table part. It would use this table scan. This is how many rows it will produce. This is the cost of it. Then let's see, table part-sup is added. Then there are 3 ways to read it. It picks the best of them is ref axis on table. The best of them is ref axis, and but it shows that it has been pruned by cost. Yeah, so this is how you can view the details. So join optimizer takeaway. Consider execution path traces the join order choice. It can get very large, so you have to use grep for plan prefix. Best join order will show the final prefix. By the way, hardcore JSON path users might want to, instead of grep, use searches like JSON extract and then use a filter. Unfortunately, one can't do this because MariaDB's JSON path implementation doesn't support filter. And neither does MySQL's, by the way. So you'll have to use grep and get a good text editor to navigate this very large document. So things we've covered so far, we've covered ref axis, rows, part of rows estimation, join optimizer. Well, there is a lot more in the optimizer trace. There are rewrites, various rewrites and transformations like view, CT merging, into exist subquery rewrites, min max transformation. Then at collect table statistics, there is it reads data from histograms and tries to estimate selectivity. It searches for constant tables. Some tables are marked as constant. It shows the trace shows that. Table elimination optimization eliminates some tables and it shows that. Then there is a conditioned filtering optimization, which we will see what filters are applicable for which tables. Unfortunately, this is all outside of the scope of this talk, but I hope you're getting the general idea about what kind of content is one can find in the trace and how to make use of it. Now let's look at the optimizer trace in MySQL. Now I don't want to have some kind of a match about which one is better, but I'm a big believer that we should, if there is something related or something that we could draw ideas from, we should look at it and discuss which of the implementations is better and how we could benefit. So optimizer trace in MySQL is similar to MariaDB in both user interface and the trace structure and the elements you find in the trace. There are, of course, differences. First is that the optimizers are fairly different, so there are different things printed. Also, there are slightly different set of things being traced. So while the traces will resemble each other, I don't think just running diff might be hard. And then the tracing module in MySQL has extra features. So let's review them and see if there is anything we could learn from MySQL's implementation. So the extras in MySQL, the first one is that it can capture multiple traces for nested statements. If a statement invokes another statement, which can be done with a stored procedure when statement uses, MariaDB will only save the trace for the top level statement, while in MySQL it will actually save the traces for substatements as well. This is controlled with optimizer trace of set and limit, so you can set it to save first or last end traces produced inside the statement. But the issue here is that basically there is no other support for troubleshooting nested statement. For example, you can't get explain output for this substatement. You can't get the statement time, how much time the statement has executed. Well, in some cases you can infer the statement time and even number of rows examined from performance schema tables, but this only works if your stored procedure is very simple and doesn't have any complex logic. Because if it does, it doesn't show you the statement text, so it will be really hard to figure out which statement it has in mind. So my takeaway is that I don't think this is useful in this current shape. If you have optimizer problem inside stored procedure, the practical way would be to take away that statement out of stored procedure and troubleshoot it separately. The second extra feature in MySQL, one can omit parts of the trace. They have optimizer trace features variable, which is a set of flags: greedy search on off, range optimizer on off. These you probably recognize. Dynamic range on off, repeated subselect. So you can switch these off and then the trace will not be saved for those. Well, my answer to that why would you want to turn them? It's not an issue. The issue is not with the trace sizes as such. The issue is we want to look at only particular parts of the trace, and typical workflow would be to use JSON extract to get the part of you need, rather than using flags to chop off the parts that you don't need. I agree that the flags would be useful for some global settings, like let's print cost values or don't print cost values if you don't care about cost values, which apply to all elements in the trace everywhere. In other words, I don't consider this. This is something we could add, but I don't think it's very important or very needed. Yet another extra is in MySQL, one can control the way JSON output is formatted. The first thing is that you can set one line flag to on in the optimizer trace variable itself, and in that case you will get trace in one line, which will probably make it take less space, but again, I personally never saw any need for it. The other one is that you can set, there is a variable called young markers in JSON. If you set it to true or on, you will have these young markers, so steps. When the array yans, you will have this comment indicating that this is steps ended, and so forth. Well, this improves readability somewhat, so somebody might find this useful. My issue with this is that JSON actually doesn't allow comments. So if you set this on, the output is not a valid JSON anymore. You can't pass it to JSON extract, for example. And maybe this should not belong to some global variable, which suddenly makes JSON something non-JSON, but rather a function which prints it. It would also add something to make it more readable. Yet another extra is that tracing in MySQL covers some parts of the query execution. Most notable users file sort. For example, if you want to know whether file sort is using priority queue optimization, this is not shown and explained. You can only get it into if you enable the trace and run the select, not explained, but select itself. This also shows like a memory available and other details. And well, my guess is that MySQL had to put it somewhere. They couldn't put it in explain for technical reasons, and they didn't have explain analyze back then, so they had it save it in the trace. This is actually not a very good idea, because if the file sort is done in subquery, this will produce loads of repetitive JSON, and that's why they needed to disable it here in repeated subselect to avoid producing really large JSON documents. Well, in MariaDB, this kind of information is shown in analyzed format JSON output, which is the command specifically targeted at collecting runtime statistics. So we don't have and don't think we should have this in the optimizer trace. Analyzed from a JSON shows roughly the same information. Okay, so that's for extras in MySQL. What's extra in MariaDB? You may ask. Well, in one word, just like I would say, more polish. We were trying hard to eat our own dog food and use trace for performance troubleshooting we do. So things that we did, we made printout of conditions more readable. Here's how condition looks in MySQL, and here's how it looks. The same condition looks in MariaDB. This may not look like a big thing, but this amount of ridiculous overquoting makes conditions really hard to read, especially when the query is large and conditions are long. Well, we saw that data constants are printed as hex, not dates. We fixed that. The important thing did other similar smaller fixes. The important thing is that MySQL actually prints incorrect for range analysis for multiple key parts. We had a similar problem. We made the similar mistake in MariaDB, but we had caught it and fixed it before we released. Here is a bug in MySQL which shows that I reported it to them, they didn't seem to care. So conclusions. Optimizer trace is available in MariaDB. It shows details about query optimization. You can analyze it yourself, or you can save it and submit traces when discussing or reporting the optimizer issues you encountered. MySQL has a similar feature that has some extras compared to MariaDB, but they don't seem to be important. Our future plans mostly is about printing more useful information in the trace. We don't want to print everything there to flood it with content. It's already quite large, but we want to use our experience to find what would be useful and add printouts for that. So submit us, if you encounter optimizer issues, submit us them to us together with traces, please. So that's it. Thanks for your attention.